So let's continue today. So as I mentioned, let's first probably see if we can, let's discuss the project first, the problem statement, and then we can, if we have time, we'll continue with the rest of the theory. So again, I just did some background work. So I'm choosing, this as I think 2 different specs were given. I'm just choosing this as an example because I believe a lot of you complained to 20 picofarad was difficult to drive. And I think this was the spec given, right? Yeah. So first of all, tell me, if I say that the output has to be, I mean, the op amp has to drive a resistive load, can I use a single stage or I need multi-stage? So that much was clear. This has to be multi-stage. And I also mentioned this has to be a general purpose op amp. Multi-stage requires compensation. So what compensation would you use? So at least these two are clear. So this might be the starting point. I have a 2-stage Miller OTA like this. Okay. Of course, by this time you would have recognized you need to have Cascode somewhere to get the gain. It's okay, but let's start with something simple. With this structure, I should be able to meet all the specs except the DC gain. So first, let's see if we can do that. And these are the other 4 specs. I need to get a loop gain of 80 dB with this feedback factor, phase margin greater than 70 degrees, and closed loop bandwidth of 50 megahertz. Right? So I did some initial calculations to save time. So let's walk through that. These are the specs. So again, I started with phase margin as a spec, and worst case phase margin occurs for what value of beta of 1. So that's why I'm considering this. And phase margin for 2-stage Miller OTA is this. Ignoring that zeros sort of cancel, we'll take care of it. So this sort of gives you your second pole to be roughly at 3 times the unity gain frequency, and also the closed loop bandwidth is 50 megahertz, and that's approximately the omega u loop. So beta times the GM by CC is this much. So you know what is P2? This is omega u. I mean, it's not clear. This is omega u. From this, we can straight away get what should be your second pole location. This much I'm sure everyone would have done, I'm assuming. So that's why I'm going through it quickly. And second pole location is approximately GM5 by CL, where GM5 is essentially the second stage. And remember, this is assuming that the capacitance at the output of the first stage, I mean, this is C1, right? And what is this majorly contributed by? The total cap here is majorly dominated by which parasitic cap? The gate capacitance, so I'll call it CGG5. Okay. So the second pole is approximately GM by CL if the gate parasitic cap is smaller than my compensation and load cap, and also load must be greater than the compensation cap. These are the conditions under which this approximation is valid. Remember? So I already know my load is 20 pico. So to use this approximation, I am restricting my CGG to be 10 times smaller, let us say, so 2 picofarad. Reasonable? And I also need to choose my compensation capacitance. That is it. Yeah. My compensation capacitance must also be greater than CGG. Okay. Because remember, ideally you have something like this, right? The exact pole location is GM5 into CC by C1 plus CC. This is the exact thing, right? Only if the compensation capacitor is greater than C1, I can say that this is GM5, right? So I am trying to choose CC greater than CGG, but I cannot choose it so large because my load cap is already 20 pico. So I am choosing this to be slightly larger, 5 picofarad. So which means my assumption that CC is much greater than C1 is not valid, right? So I'll use the proper expression here. I mean, are you guys able to follow? Right? This is just basic calculation which I'm hoping you are comfortable with. That's why I'm walking through it quickly. So in my assumption, CC was 5 pico. This was 2 pico. I plug in the values. This is what I get. So instead of GM5 by CL, it is now 5 by 7 times GM by CL. That's all. So these are the final results. So second pole is 5 by 7 times GM5 by CL, and we know this location already. And from this we can find GM5. That's 160 millisiemens. And I already restricted my CGG5 to be 2 picofarad. That's what I've assumed it to be. So once I know GM and CGG, GM by CGG for this transistor is fixed. So 160 by 2 pico, that is about 80 gigaradians per second. Okay, one thing is, if you evaluate GM5, this comes as 130 millisiemens, I believe, but I chose it to be a slightly higher value, 160 millisiemens, just to be safe. Okay. So now I know GM by CGG, I can find out these two parameters. So let's quickly do. Let me see if I can. Yeah, again, see that first I have like drawn the schematic. That's what I'm saying. Wiring the schematic is very important. Wire it the same way you draw on paper, so that way it becomes clear what is what. And if you see, I would also have named the transistors M1 here, M2, same, this will be M3, M4, M5. So that way it will also be clear which transistor you are referring to. And I have created proper test benches like this. So we'll come to this. So let's look at the GM by CGG plot. So I think I have it here. Yeah, this is the GM by CGG versus ID by W in the x-axis. So how much I wanted? 80 gigaradians per second. So let's push it. Yeah, somewhere here. 80 gigaradians. So the ID by W I get is 34.6, right? So let me just do it. If anyone has a calculator, please take it out and help me calculate, or take your phones and calculate. Okay, I also need GM by ID, so let me do that. GM by ID should be here. Yeah, this is GM by ID, I believe. GM over ID. I want ID by W of 34.6, so let's me somewhere here. 4.18, roughly 4, let us say 4.18. Let's do it. Yeah, so now can you help me calculate what is GM is 160 millisiemens. Yeah, what is I? 160 by 4, so roughly 40 milliamps, let's say. Help me calculate W then. Current is 40 milliamps. ID by W is 34.6. 40 milli by 34.6. How much is it? 1.5. What is the third decimal? 6. Okay, 1.156. So much millimeter. Huh? Yeah, millimeter. I mean, it's actually quite wide in practice, but it's okay for the project. It's okay. So yeah, and also this is fine. Now we have found out the current and width, but I also need to make sure the operating point VGS is fine, so that transistors or other stages are not affected. So let's look at VGS. This is VGS. So at the same 34.6, that's about 900 millivolt, right? 880 millivolts. So which is reasonably good. So what that means? There is a schematic. Yeah. So this is 1.8 volt. The VGS for this is 0.9 volt roughly. So this I expect it to be roughly at 0.9 volt. So this should be sufficiently fine. So this I fixed as 40 milliamps, and this is 1.156 millimeter, and I use minimum length. Okay. And if I know properties for this PMOS transistor, what else I can find out? Is the properties for some other transistor known now? Yeah, these two PMOS are also set. They also have the same current density, 34.6 ampere per meter. Okay. Cool. Now the only thing pending is this PMOS, sorry, this differential pair, and I also did background for that. Yeah, you remember we already know GM1 by CC is so much, so that I directly take it, and I already assume the compensation cap to be 5 pico. From this, this is what, can you calculate this? I didn't calculate it fully. So 2 pi times 50 mega times 5 into 5 pico. It's 250, 1.25, 1.25 into 6, 7 or something, 7 or 8. 12 7s are 84. Less than 8.4. 7.853. Okay, so roughly let's round it to 8 millisiemens. Okay, cool. Now to sizes I need to know at least one of the parameters. So you can assume, I mean now, okay, there is no constraint, so you just have to assume something and move on. You can assume VGS or something. I'll assume, let us say GM by ID. Say I'll assume it to be. No, we don't know for first stage, right? No, this is for the differential pair. I mean, we are right now doing for the diff pair, right? For this we don't know anything. We have just found the GM because we know GM by CC is the bandwidth, From the bandwidth spec we got GM. So I need to do the rest of it. So I'm assuming GM by ID. You can do anything. Okay. So I'm assuming to be some 10 roughly. So what is ID? 800 microns. Yeah. Then okay. Then I need to find what is ID by W and VGS. So let's do that. I assume GM by ID of 10. So this is for the PMOS. So let me plot for NMOS. This is for the NMOS. Yeah, this is for the NMOS. This is GM by ID. I want it to be 10. Okay, this what I'll increase this. Yeah, you can see it hopefully. So about 10. Yeah, about 14.7 or something, right? This is GM by 80 is 10. Sorry, no, GM by 80 is 10, right? Yeah, 10 is somewhere here. Yeah, this is about 10, 10.0. So the ID by W I get is 28.2. So can you calculate the width? 28.2. ID is 800 micro, so 800 by 28.2. Let's say 28. Let's also make sure VGS is fine, because if VGS is so large, then you will get troubles with this fellow, right? Because as of now, this is at 0.9 volt. If VGS is really large, this voltage might become so low. So let's make sure if things are fine. So let me also plot VGS. I already have it. Great. I should look at the same thing. So 28 point something. Yeah, about 640 millivolts or something. So 640 millivolts. So which means this is fine. This is at 640 millivolt. So this will be roughly 0.2 volt or something, right? 0.26 volt or something, or how much? Yeah, 0.26 volt, roughly 0.2, let's say. So this should be reasonable for this current source. So now we have sized everything. Let's actually go on to it. Okay, this also needs to be this is pending, right? The PMOS transistor. The current is 1.6 milliamps here. So 800 microns is the current flowing in the PMOS. ID by W is 34.6. So width should be 800 by 34.6. How much is that? 23.1. So let's fix it to be 23. So width of the PMOS transistor is 23. Again, I've chosen all minimum lengths. Okay. So let's actually put the values and see what we get. So okay, so this I've already set the values, I think 40 milliamps. Okay, so this we got has how much? 1.156, right? Something like this. Yeah, 1.156. So I'll basically think what I've done is this. Yeah, what I've done is I've essentially put 578 fingers and 2 multipliers, which means the total width is 578 times 2. That's 1156. I mean, we'll come to what this means when we do layout, but as of now, we can assume that 1 micron times 578 times 2. That's the total width. So that's 1156 done. So this is, let's say, 5 pico. Okay, so 5 pico is set. And let me instantiate things and put it quickly. The current is 1.6 milliamps. And how much for the diff pair? 28 micron. So let me erase all this and put it. So I'll assume a finger of 1 micron and 28 fingers, so 28 micron. And the last PMOS was 23, right? So 23 fingers, 23 micron, done. Okay, so this is what I have designed. First, let me run DC operating point and see how things are. Let's see if it runs fast. Okay, it's going to take some time, I think. I don't know why. But till this point, I'm sure everyone would have done the design, something like this. So let's see. Oh, it's taking so much time. Oh, perfect. Okay. If you are lucky by the end of the okay, yeah, nice, got it. And it do this. So let's take the operating points. Yeah, this I wanted it to be about 900 millivolt, so 920 millivolt. Yeah, this was 200 millivolt. That's what I get here. Okay, let's check the properties, GM and stuff. So let's say this guy. Yeah, GM I wanted to be 160 millisiemens. Here I get 168. Well and fine. For the first stage, I wanted GM of how much? 8 millisiemens. So here, yeah, the GM I get is 8 millisiemens. Right, spot on. So hopefully we are fine. So let's check the stability and phase margin and stuff. So first I will check the stability with unity feedback. So again, now you see what I have done, right? See, I have created two test benches here, properly commented them. This is how in practice a good schematic is done, right? If you go to the industry and like make transistors randomly and they'll just say this is not I want, okay, they'll just throw it out. So make sure you, whenever you make something, make sure it's nicely commented so that it becomes easy for someone to understand, because it's not like this design will be used only by you throughout your life. Someone else has to use it for some other application. So that person should be able to understand what is happening, right? So I've created test benches, wired the same way we draw it on paper. This is unity feedback. This is with the inverting amp with a gain of 4. So let's check stability. Let me select this probe. Okay, let's see what we get. Oops, sorry. Yeah, okay, done. Oops. Okay, so let's check the stability summary. Yeah, phase margin of 74 degrees, which is okay because I wanted 70 degrees. Now let's check the stability in feedback factor of 1.5 in this 4x unity gain. I mean 4x gain. I think that's where everyone had issues. Let's see. Sorry, very good operating point. Stability. So now we straight away see this is phase margin is 33 degrees. The unity loop gain frequency is 23 mega. Not great. And of course, this is sort of expected. Why? Huh? Sorry, one more? Yeah. I mean, yeah, I think everyone recognized it. We also discussed in the class. So let me see if I can write it. We have the structure. Oops. So when you try to find the loop gain, input is shorted. Now you have a parasitic capacitance here. Let us say call it Cp. So this is, let us say, R and 4R. Yeah, and this is going to introduce additional pole. So what was the fix to correct for this? You add capacitor across 4R. What should be the value of the capacitor ideally? Cp by 4. That much was clear. So let's put that and see. Further, I need to know the parasitic cap. So let's check the operating point and see. CGG, that is this. CGG is about 50 femto. I don't know if you can read. 50 by 4 is how much? 12.5. So 12.5 femto. So let me put it across this fellow. So now let me run this. Okay. So stability, yeah, now at least phase margin has definitely gotten better. Expected, should not be surprising. Unity loop gain frequency is about 40 megahertz. Not exactly what you want, but close. But I think let's look at the 3 dB bandwidth. I think that's where the catch comes. Okay, I'll close this actually. Is it now? Okay, closed loop starts at 12 dB. Makes sense, 4x gain. And I should look at what point now? 12 minus 11.9 minus 3, 8.9. So 8.9 somewhere here. So the bandwidth is about 12 megahertz. So yeah, I'm sure everyone faced this issue. You didn't face it. Okay, if you face it, you have designed it fine. So why do you think that's happening? Okay, first of all, tell me, let's look at the situation we have. So we knew that this is all happening because of this parasitic cap. That much was clear, right? With respect to the loop gain, it seemed as though if I put this cap here, this worked nicely. We got the required phase margin. But if I look at the experiment of calculating the closed loop bandwidth, wherein I have the setup this way, I apply the input here. I have this fellow. So once again, you have a parasitic cap here, and you are trying to compensate for this by putting cap here. Let's call it feedback cap CF. Okay. So two observations. One, to tackle the effect of this parasitic capacitor, if I add a feedback cap, seems like my phase margin is sort of good and my unity loop gain frequency is close to what I want. That's something we all expected. But in this experiment, it's not happening. Bandwidth is pretty bad. So tell me why in the first place this this even works. That is, if I have a capacitor of Cp by 4, why do you think this even works in loop gain? What was the thought process behind adding a cap here? Yeah, you're sort of adding a 0 again. If I just look at the feedback network alone, this is in the loop gain picture, right? In the loop gain picture, I have, if I just separate out the feedback network, I have something like this. This is R and 4R. Now, if the capacitor was not there, the parasitic cap was not there, then what can you say about the transfer function from this to this, the feedback transfer function? 1 by 5. This is 1 by 5 across all frequencies, right? That's the important thing. Okay. So if I'll try to see if I can make space. Yeah, if I try to sketch it across frequencies, I'll basically get, sorry, yeah, I mean, not able to draw it neatly, but yeah, it's going to be constant 1 by 5 across frequencies. Now, the moment we saw we have a capacitor here, what will happen to the transfer function now? What do you expect will happen to the transfer function? I mean, qualitatively, as an increased frequency, what do you expect to happen for this transfer function? It will start to roll off, and that's what was impacting you. Now, to correct for it, what was the idea? Yeah, why was the capacitance helping? Let's say you put a cap here, and if you choose this capacitor to be the optimal value of Cp by 4, now the idea is the following. So let's say if I put Cf as Cp by 4, see, earlier when I didn't have the capacitor, the transfer function was essentially an impedance division between two identical elements that was constant, so no frequency dependence. Clear? Now if I have the parasitic capacitor, that's no longer the case. The impedance division happens between a resistor and an RC section. Now the idea is to restore and make it flatten again. You introduce a capacitor so that it appears as though I have two RC sections. Both of them are exactly scaled by a factor of 4. Right? If I do that, once again, you expect that the transfer function will be restored to 1 by 5. That is constant across frequencies. This was the expectation. And it worked. No complaints. So don't complain that what I taught is not working. It works definitely for loop gain. Now, it appears this is not working in this case. So now, based on what we discussed now, can you tell me, does it make sense that it is not working here? Or maybe I'll start this way. So let's say I don't have this parasitic cap. This is also not there. What do you expect for the transfer function across frequency, the closed loop transfer function? -4 magnitude alone, it's 4. Let's say op amp has no poles at all to start with. It's going to be 4 across frequencies. Now, let us say you have a parasitic cap here. So this is going to sort of cut off your bandwidth. Now, you are saying that to tackle it, I'll put a capacitor here. So now do you think that will help now? I mean, in the earlier case, in the loop gain picture, why was it that the transfer function got flattened? Both impedances, the two impedances that are in play, they are exactly scaled versions of each other. Okay, that's clear. In the loop gain picture, the two impedances which are essentially taking part actively, they are scaled versions of each other. Now, in the closed loop gain calculation, what are the two impedances that are in play? I mean, to find the closed loop transfer function, let's ignore the cap also. How do you find the closed loop gain here? Assume an ideal op amp. What determines the closed loop gain in this? Hey, come on guys. I mean, let's say I don't even have this. How did you say the gain was 4? Yeah. Finally, what impedances are important? So this fellow and this fellow. Now, if I add a CF here, I'll essentially be looking at this RC impedance and this impedance connected from resistor to the virtual ground. Now, of course, I have parasitic cap here. Now, see, remember that for this to flatten out, the two impedances must be scaled versions of each other. In the loop gain, it was happening. In the closed loop picture, this RC section is one impedance. The other impedance is just this R. So, do you think it will help now? Are you guys following the argument? So, does it make sense that now it will not help? No, the idea is, see, you are trying to understand the solution and try to, you have a hammer, use a hammer to solve all the world problems. No, that's not the case. See, here it worked because of the following reason. The two impedances which are actively participating in your transfer function, they became exactly scaled versions of each other, right? Whereas here the two impedances that are in picture are this RC section and this R, correct? They are not scaled versions. To make this scaled version of each other, what should I change here? I add another C where? Yeah, parallel to R. And if this is CF, what should be the value of this cap? 4 CF. Correct. Now you will find that this exactly scaled versions of each other, you will be fine. But of course, now you should also make sure in loop gain it is okay. So now if you add this extra cap CF, in the loop gain picture, it is going to come like this. Now the total capacitance that will be in the sections will be CF and CF plus CP. Now in my closed loop, I want these two to be scaled versions. Same thing I want it to be. I mean, same thing I want in my loop gain picture also. So if that is the case, what can I say for CF and CP? I mean, let's say I call it CF, 4 CF and CF here. So if in this picture also, I want this section to be approximately 4 times this, how should I choose the value of 4 CF and CP? CP should be? Yeah, CP should be 0. I mean, CP cannot be made 0, it is there. So what is? Yeah, you try to keep it this way. That's all. All you have to do is go and put a larger capacitor that dominates CP at this section. So which means you still have the same thing happening in your loop gain. Phase margin will be fine. The act of putting this capacitor will improve your bandwidth. Does it make sense? Okay, if you're not convinced, let's actually see it. I hope it works. Let's see. So my CF, okay. What's happening? Okay, cool. So now I'll try to add the capacitor. So what I'll do, I'll make this say 100 femtofarad. So which means I'll go and add, what should be the cap I add here? 400 femto. Arey, missed this. Fine. So now let's verify things are okay. So let's check the stability. Yeah, phase margin is same, sort of fine. Bandwidth slightly dropped to 38 mega from 40 mega, sort of expected because you had a large cap, so something should get affected. Let's not worry so much. Let's look at the closed loop. That's the important thing. So this is 12. So I should look at 8.9. Yeah, now I see that my somewhere here. I don't know if you can read. This is 39.8 megahertz. So now at least you see there is a very good correspondence between the unity loop gain frequency and your closed loop bandwidth. Make sense? So again, always try to don't try to blindly remember a solution and try to apply everywhere. It is not like I found a hammer, I'll use a hammer to solve all the world problems, I'll go hit everyone. You understand why that problem happens in that particular situation, how a particular solution helped in solving the problem. Understand that. If you understand that, then you can use it here also. Because I didn't teach anything new here, right? It's the same thing. But the fact is, how you apply this basic idea of impedance scaling changed. That's it. So anyways, now let's get back to this. So bandwidth is slightly small. So let's try to increase the bandwidth. Bandwidth depends on what here? Bandwidth is a unity gain frequency. It is determined by what parameters mainly? GM1 and? Yeah, so I have to increase GM1 or reduce CC. I'll reduce CC because I don't want to touch the operating point. So as of now it's 5 pico. Maybe I'll make it 3 pico. Of course, see, the moment I make it 3 pico, unity gain frequency has increased. Second pole is still the same. Phase margin will slightly get a hit. So to counter it, I'll also have to increase the second pole location, but we'll come to that later. Let's at least make sure if the bandwidth is improved. Okay. So let me plot the closed loop picture. This is 11.9. Yeah, so 8.9 is somewhere here. So bandwidth is, I don't know if you read, 66 megahertz. So easily achievable. I mean, okay, if you're not able to read, please trust me, it's 66 megahertz actually. Yeah, but let's look at the phase margin. Okay, phase margin is good here, 85 degrees. Let's also verify the phase margin in unity feedback. That might take a hit. So I'll select this probe. So let me check the stability summary. Yeah, phase margin now has slightly come down to 66 degrees if you see. Sort of expected because they increase the unity gain frequency, keeping the second pole same. So what can I do to counter this? What should I do? Yeah, increase second pole, which means you have to increase GM2. So I'll essentially scale both the current and the widths by the same factor so that operating point is untouched. Okay. Current and width is scaled by the same constant, ID by W is same, so rest of it will remain the same. Noise is from the AC, is it? So right now it's 40, so let's say I make it 1.5 times larger. Again, I'm randomly doing, I mean not randomly, I'm sort of putting the scaling factor in a tentative way, but if you're actually designing, you exactly compute how much will it degrade by, and you can exactly put that scaling factor. Okay. So let's see, yeah, stability, yeah, phase margin is now 70 degrees, perfect. Let's also verify if we have maintained the same phase margin in the other feedback configuration also. So I'll check in this. Yeah, here also it's 86 degrees phase margin, so we are set. Let me check the closed loop bandwidth, that should be same. So 11.9 to 8.9. Yeah, 8.9 is somewhere here, again 61 megahertz if you can't read. So we are still fine. So that's it. So now we have met all the specs. What might not be met now? DC gain, yeah. So let's check how much is the loop gain we have. I have about 38, 39, roughly 40 dB. I should get 40 dB more, not a big deal. What do I do to increase again? Yeah, I can do Cascode. So again, I don't have time, so I'll try to do it slightly in a more tentative fashion. So as of now, what is the situation I have? See, I'm sure DC gain was not the problem for you guys to meet, right? The main problem must have been this bandwidth, and I'm sure that was because you didn't recognize this. Okay, OneNote is not responding. Okay. Close. Let me open it. Okay, what is the operating points I have? Okay, this is 900 millivolts. Tail node is at 200 millivolts. Okay, let me write it directly. Oops, sorry. Okay, so as of now, let me try to put a Cascode for the NMOS first. For the NMOS, as of now, the situation is this. This is at 0.9 volts. This is at 0.2 volt. The output is at 0.9 volt. So I want to put one Cascode. So let me try to put one Cascode. Okay. So I think threshold voltage in this process is roughly 0.5 volts. So the VGS is 0.7 volt. So which means the overdrive voltage is 0.7 minus 0.5, 0.2 volt. Okay. Now I'll try to do some random things. I mean not random, directly I'll try to do. So I'll try to fix the overdrive of this transistor to be 0.1 volt. So I'll size this to be 4x so that the overdrive is 0.1 volt. Okay. Now if this is 0.9, what is the lowest this can go? The gate is at 0.9. The drain can go at the minimum how much? One threshold lower, so 0.9 minus 0.5, 0.4. So I'll try to keep it at roughly 0.5 for to be safe. So this is 0.5 volt. Overdrive is 0.1. Right? So this should be 1.1 volt because. Okay, fine. Similarly, I have the PMOS transistor. PMOS, I have something like this. This is the main transistor, 1.8 volt. Gate is at 0.9 volt. This is also roughly at 0.9 volt. So I want to add a Cascode here. So this is 0.9 volts. So source to gate voltage is 0.9 volt. So overdrive is how much? 0.9 minus 0.5 is 0.4 volt. So I will try to keep overdrive of 0.1 volt for the Cascode also. So which means this is 0.4 volt. If the overdrive has to be 0.1 volt, how should be the width of this transistor compared to this? 4x or something? I want to change the overdrive by a factor of 4. How much should the width increase by? Current is W by L into overdrive square. I want to keep the same current, reduce overdrive by a factor of 4. 16x, is it fine? So we'll make it 16x wider. So let's fix the gate voltage. So this is at 0.9. What is the minimum this gate can drop to? Threshold voltage is 0.5 roughly. 0.9 volts. What is the minimum the gate can drop to? 0.4 volt. So I'll keep it safely at 0.5 volts. So NMOS I am going to size it to be 4x wider than the diff pair. PMOS 16x, 1.1 and 0.5. So let me just quickly do it. I'll just put it on one side for now and verify what's happening. So this has to be 16x, so I'll multiply it by 16. Sorry, NMOS is 4x, right? 4x. And for now I'll use ideal voltage source to bias. This was 1.1 volt. Here for now I'll keep the voltage source here, or maybe I'll shift it. Let us say this is VB, VB of NMOS 1 and GMDA. Now similarly for the PMOS, I told it was 16x. So 16x I'll multiply. The gate voltage was 0.5. So let's call this VB. Okay, so now let's see. I'll just put on one side and see if the operating points are as I expect, and check if the gain is fine. Okay, let's see. I don't know if I'll have time to do it fully, but let's see. For sizing Cascode, you don't have to follow the way I did. You can actually fix what is your overdrive voltage. Look at the GM by ID plots and do it. That's a better way to do. Since I don't have a lot of time right now, I'm sort of directly doing it. Sorry, I should look at operating point. So let's check operating point. I wanted this to be at how much? Yeah, 0.5 volt. This is at 0.45 volt. Okay. You can see, right? 0.45. So this is okay. And okay, so now this will be at what volt? This is 0.5. Overdrive I've chosen to be 0.1. So VGS is 0.6. So this will be at 1.1 volt, right? So this is also at roughly 1.06 volt, close enough. Let's see how much has the gain improved by. Hopefully by 20 or 30 dB. Let's see loop gain. It has gone to 60 dB. I don't know if you can read, but 60 dB. So still 20 dB short. What can I do now? Where do you want to put Cascode for second stage? I can put a Cascode in the first stage also, right? Who stops you for putting one more Cascode here? Remember you have a supply of 1.8 volt, right? Even if you assume overdrive voltage of 0.2 volts for all transistors, that is the minimum drain to source of 0.2 volt. How many transistors I can stack here? 9 transistors, right? So which means even if you discard 1.2 volt for your tail current source, if this takes 1, you can still put 8 transistors in this, which means you can put 4 NMOS cascodes and 4 PMOS cascodes. You are still fine. The supply voltage is actually quite big. You can actually nicely play around. You don't have to go to all gain boosted cascode and stuff, right? Understand why that was used. Again, just because something is known to you doesn't mean I found a gun, I'll shoot and take it and shoot it and solve all the problems, right? Use it when it's required. The gain boosted cascode was required. Why? What was the advantage over putting normal cascode? swing limits, but here you are okay. It's a first stage. First stage is not going to swing, and I didn't give any constraint on swing limits. So who stops you from putting one more normal cascode? That's easier, right? So let's do that and see if we can finish it on time. So let's say this is what I have right now. So which means I need to put one more. So this is 0.5. So I'll try to put one more cascode here. Let's say I do the same thing. I size it to be 4x. So overdrive is 0.1 volts. VGS is 0.6 volts. Right. So this I'll fix it as 0.5 volts. So can I do? This I fix as 0.5 volt. This becomes 1.1 volt. This is 1.1. What is the minimum the drain voltage can come to? 1.1 is the gate. What is the minimum drain can come to? Threshold of 0.5. 0.6 volts. Let's keep it at 0.7 volt. So VGS is again 0.6 volt. So this should be 1.3 volt. Okay. I mean, if I use identical transistor, that's what I'll get. Same thing I'll do for the PMOS side also. So I mean, here I see that. Okay. Let's see. Okay. Amazing. Yeah. Even for the PMOS, I'll do the same. I'll put one more identical device here. Okay. I'll put one more identical cascode. So earlier this was at 0.5. I'll keep it at 0.7 and it should work. Okay. Because I'm following the same idea. Here earlier it was 1.1. I put another cascode device. Increase the gate voltage to 1.3 volt. Voltages are fine. Same thing will happen here also. I'll use same 16x size transistor. Earlier the cascode was biased at 0.5. I'll put one more with 0.7. So you can think about it. I'll just do it quickly and wrap up. So this will come here. So I'll make it VVP2. So this I'll keep it at 0.7. So similarly, I'll use the same 4x sized NMOS. This I'll keep it at 1.3 volt. Okay, now let's verify. Okay, let me plot the loop gain. Oops, I made some mistake. What happened? Okay, sorry. This is, I changed the voltages. So got this down. What happened? I did some incorrect thing here. So this is 1.3, this is 0.5, and this one 16x. What changed? Oh, yeah, correct, right? This is at what's happening? So I expected NMOS side is fine. I have 1.3, 0.6, 1.1 and 0.4. The PMOS side, I expected how much? 0.5. I make a connection mistake. Okay, this is at 1.8. Why is it at 1.8? Did I make any connection change? Sorry, I think I made a mistake there. Nice. Sorry, I kind of shorted the, yeah, I made a mistake, sorry. By mistake shorted the supply to the drain. So let's see. Now it should hopefully work. You guys have a class at 10? No? You have a class, huh? Okay, just a couple of minutes. Let's see. Okay. Plot it. Yeah. So now 70 dB. You can put one more Cascode and increase it. But why this should have worked? I don't know why. I keep changing the voltages. I'm really sorry. I change the bias voltages. Just give me a second. But hopefully you get the idea of how things are done, right? That's the whole point. I mean, this spec is easily meetable. It's not like impossible to meet. So hence proved the project is solvable problem. Okay. Let's verify if the gain is fine. If so, we are set. Yeah, now your gain is 81 dB. You are fine. Let's check the stability. 85 degrees. Perfect. Closed loop bandwidth. This is at 11.9, 8.9 somewhere here. If you can read, it's 57.5 megahertz. Bandwidth is also met. Done. Let's also verify if things are fine in unity feedback. That's the last thing. Sorry. Because I added a lot of Cascode, so some parasitic poles might be added. Phase margin might slightly degrade. So if phase margin degrades, what can you do? No, phase margin is, remember phase margin depends on unity gain frequency and second pole, that's all. Now if you want to improve the phase margin, what can you do? Yeah, increase GM2. I can scale GM2 further, that's it. Let's verify if things are fine, we are okay. Yeah, phase margin became 66 degrees from 70 degrees. So I can actually go and increase GM2. Let's say right now I have 1.5. So let's say make it 2x. This also will make it 2x. So now it should be fine. Right now because of severe lack of time, I'm randomly making it 1.5 to 2. But actually go and calculate, okay. But this is how I might go and solve, right? Stability, yeah, 69.7, 70 degree. Okay, 69.7 is 70 degree. Okay, it's okay. If you want, you can increase it further, right? You can trust me, right? You can increase it further if you want. From 2, you can make it 2.1. Closed loop bandwidth also, let's verify. This is 12 and about 9 dB. Yeah, you still have 53.7 megahertz. And this also. So I'll stop here and